daar ga ik. Yes, I think we are live. Welcome all to the epic enzyme webinar of Campus Groningen. My name is Sven Stielstra, business developer at Campus Groningen, and I will be your moderator for today.
Te snel.
Yes, I think we're live. Welcome all to this epic webinar regarding enzymes of Campus Groningen. My name is Sven Stielstra, business developer of Campus Groningen, and I will be the moderator of today. This means that I will guide you to the program, and I will be the linking pin between you, the audience, which are viewing this via the YouTube live channel, and the speakers over here. So if you have any questions, put them in the chat box and I will pass them through to the speakers. Right. First of all, the goal of this webinar is, on the one hand, inform you about the knowledge and expertise we've got at Campus Groningen about enzyme innovation. And on the other hand, we would like to explore if this short but sweet meeting can be the start of some new collaborations between you, the companies that are watching, but also research institutes and our ecosystem of enzyme engineers, of enzyme experts, I should say. For us, this is the first time to organize an international meeting in this way. Normally, you are more than welcome to meet us all in real life at Campus Groningen. But unfortunately, the COVID crisis forces us to be creative and reach out to you via different ways, like this webinar. The program of today is I think we have a quite packed program for the coming hour. We start with Edward van der Meer, Director of Campus Groningen. He will introduce you to Campus Groningen and its innovation infrastructure. He will be followed by Professor Marco Fraaije of the University of Groningen, which focuses on fundamental research on enzymes. Hugo van Beek, COO of Gecko Biotech. Linda Dijkshoorn, CEO of Evie Biotech. Then we have a duo presentation of Dr. Doede Binnema and Professor Gert-Jan Euverink about scale-up facilities and scale-up projects regarding biotech and enzymes. And we finish off this webinar with Elena Herrero Gomez, Business Development Director of Mercagem Syncom, and she will go into Chiral APIs through enzymatic catalysis. All right, we have a packed program, so I should say let's start with the first speaker of today. That's Edward van der Meer, Managing Director, Campus Groningen. Edward, I think the floor is yours.
So thank you, Sven. Welcome to Campus Groningen. My name is Edward van der Meer, and I will tell you more about the innovation ecosystem of our campus, where researchers, entrepreneurs, and talents work together to create real impact. So, first, an impression, where is our campus located? Well, it's in the Netherlands, as you can see on the map, and we are located in the north of the Netherlands in Groningen. And Campus Groningen is located in the city of Groningen, and the city of Groningen is a dynamic city with a lot of talent. Groningen is a city with 230,000 inhabitants, and besides our knowledge institutes, there are almost 200 companies located at our campus. This gives space for 20,000 jobs and 45,000 students. So, what do we mean with a campus? What is a campus? A campus is a physical location with an interaction between companies, local government, and knowledge institutes. Together, they are working on innovation in an open environment. And my job as a campus manager is to give access to human capital, real estate, test facilities, excellent knowledge, and finance. And we believe that the best way of giving access is work in a so-called innovation train. So the innovation train always starts with excellent knowledge, and then we try to combine this excellent knowledge with a company. This leads to a project for, let's say, a startup or an existing company, and then they can make use of our incubator programs or our accelerator programs. We call it our portals. From there, you can make use of our facilities, such as our inner labs, or we can provide you with funding. There are sometimes possibilities for non-dilutive funding, but we can also attach you to our financing partners for equity funding. This gives you the chance to scale up the project and create a lot of impact. Of course, there are a lot of facilities, but for this webinar, I would like to emphasize on 3 of them. So first, I would like to mention the InnoLab Agri-Foods and the InnoLab Chemistry and Engineering. These are both facilities for lab scale innovation. The third one, what I would like to emphasize is our ZEP facility. This gives you the possibility to scale up your work on a kilogram scale. There are also possibilities for industrial scale, but we offer this within our region with our regional partner, Camport. Later on, I will tell something more about that. But in short, you can start your innovation on the Campus Groningen from a lab scale, and you can scale up in a region on industrial scale. So if you scale up or if you do your innovation, you always work within a network. We do this together with a great business network, and we connect everyone in our business network together. This gives you an impression of our business network. As I said, if you want to scale up on an industrial scale with your ideas, you can make use of our partner, Camport Europe. Camport Europe, together with them, you can facilitate and grow on an industrial scale. Campus Europe is an ecosystem for companies that are committed to develop a green chemical sector. Experienced companies, as present in our ecosystem, are DSM, Nourion, and Adventium. So, to summarize this presentation, Campus Groningen is a recipe for innovation. We hope to welcome and inspire you in our ecosystem to focus on your business doing work on enzymes. Thank you for your attention.
Right, thank you very much, Edward, for this introduction and the first presentation. A question from me to you is, you told us about the InnoLabs, Agri-Food, and InnoLabs Chemistry and Engineering. What is so special about them, and why are they so well equipped for startups? Can you tell us a little bit more about that?
Yeah, of course. I'm happy to answer that. So the InnoLab actually is a fully equipped space. So it's not just an environment with walls, but it's also equipped with equipment, and you can. It's ready to use. It also has all the necessary quality and other things that are needed for a quick start. So you can go there and start immediately.
Thank you. So really plug and play for startups.
Plug and play, but not only for startups, also for other companies. So it's actually open for everyone.
All right. Thank you very much. I don't have any questions from the YouTube live chat box, so I think it's time to proceed for the second presentation. Marco Fraaien, the floor is also yours now.
Yes, thank you, Sven. Thanks also for the invitation. I was asked to introduce academic research on enzymes at the University of Groningen for this webinar, which I will do in the coming minutes. I have assembled a few slides and to explain about what we do with enzymes with respect to university research. I would like to share a little bit of history of the university here. I think it's nice to show here that here in Groningen we were the first at the university to develop an electric car. Many people are not aware of this, even not here in Groningen perhaps, but already in 1835, Sibrandus Strating was doing chemistry at the university, and as a result of his work, he also developed an electric car. It shows that we have been doing chemistry related to machines already for a long time. And well, I mentioned the word machines. This links to the molecular machines that many of you may also be aware of, that here at Groningen University, Ben Veringa is working, who won the Nobel Prize a couple of years ago on his work on molecular machines. And again, this is, you could say, it's not really an enzyme, but at least there is an inspiration based from nature to make molecular machines. And if you think of molecular machines in nature, they are enzymes. And also on enzymes, we have been working already for a long time in Groningen. And just as a highlight, I think it is nice to show on this slide that already 50 years ago here at the university, we were one of the first worldwide to elucidate the crystal structure of a protein, specifically of an enzyme and protease, the peptide that is on this slide, done by Jan de Rent. From that time on, there has been a lot of investments made, and lots of groups have evolved to do work in the area of enzymes. It's not that every group here at the faculty is working on enzymes, but quite a bit of number of groups that do research related to enzymes or have research really focused on enzymes. So on this slide, there are the 4 institutes that harbor all the groups that have some research related to enzymes. The focus of each institute is indicated, and I also have filled in a couple of names, PIs, that have to do in some way with enzymes. So some of you may know. Also on the slide, you can see that we have a lot of facilities in our faculty to do the analysis needed to do a good level of research, which includes, for example, cryo-electron microscopy. But to give some real examples of research done here, I would like to highlight a few groups, starting with the group of Gerard Rolfes. Gerard is focusing on artificial enzymes, the design of enzymes from scratch, you could say. So he is working on proteins that have no catalytic activity, but he develops them such that they will incorporate catalytic entities like a non-natural amino acid, here in pink, or even just a catalytic ligand, a catalyst known from organic chemistry. And by incorporating them in proteins, you suddenly create enzymes that do chemistry that is not done by natural enzymes. It's a nice example of how you can develop enzymes from scratch. Another example is a group of Gerrit Poulaert, more related to pharma research, and he is focusing more on the engineering of natural enzymes, looking at them such that you understand how they work, and with the knowledge of how they work, the mechanism of catalysis, he has shown to be able to engineer them to do something useful. So like on this slide, this is from a recent work he published in Angewandte. He has engineered a lyase that can form carbon-nitrogen bonds, and he showed that this enzyme that he developed by directed evolution can be used for the synthesis of building blocks of the new generation of sweeteners, this neotame molecule. Well, as I'm here, I also could spend a few minutes on showing what I do in my own research group. My group is focusing on enzymes fully, but on this slide, the focus is indicated that is on discovery. So using new techniques, we look at, we try to find new enzymes from nature. New enzymes are also studied in detail with respect to their mechanism. And using the knowledge that we obtain, we also try to engineer them. And the engineering is more and more also supported by computational tools. And I will come back to that in a minute. And in the end, we try to show that what we find and what we design can be useful for applications, so to do biocatalysis. Here is listed a number of findings from my group that we published on. Most of them are publications, some of them are patents, in fact. It shows that we also often have work done, research done together, also with companies or in consortia within European context. But it at least indicates that some of the findings are not purely interesting with respect to fundamental knowledge, but can also be useful. And as the last topic, I would like to highlight the last finding, and that is that we have developed a method by which we can make thermostable, robust enzymes. So a computational tool has been developed in our group, it's my group and also the group of Professor Jansen, where we have made a protocol that is mainly based on computational power. So we use computers, we use software to predict what we should do to engineer, to change an enzyme such that it becomes more stable. So there is this blue picture over here, that's the structure of an enzyme, and in red is indicated what the computer told us to do in the lab, and so we did. And the result was that with 9 modifications of the enzyme, we can make a variant that is much more thermostable. You see now in the graph that the enzyme that we engineered is now robust enough to be used up to 80 degrees, while the original enzyme, the natural enzyme, can only be used up to 35 degrees. It's just one example of the development in the area of enzyme engineering and discovery. There's more and more tools available that make it possible to develop enzymes almost at will, to make them more stable, more active, or more specific. That's in a nutshell what I would like to share with you today. These slides to indicate what kind of research we do and how it is organized. And I would like to give the word back to Sven.
Yeah, thank you very much, Marco, for this presentation about all the top knowledge that is there at the University of Groningen. I think you just showed the tip of the iceberg, but one question for you is, if we are allowed to dream a bit and you have all the freedom of the world, what would be your next research project regarding enzymes? Do you have a wish, so to say?
Well, I think a wish of many in the field is that you would like to design an enzyme at will, and that you really can, for example, with these computational methods that are developing more and more, that you can really predict very accurately, very efficiently, also with respect to time, what to do to create the enzyme for a certain reaction or for a certain condition. That is something that is of interest, just to understand how that can be done the best, but also obviously this is very important for industrial application. And my dream is in fact also in a way to develop enzymes such that they can be used in applications to help also to develop new processes that can replace processes that may not be so good for the environment, for example.
All right, thank you. I've got a question from the audience, from Prasant. I probably pronounce it not in the right way, but the question is as follows. Are there any baro-tolerant enzymes for food available?
That's a good question. I know there's quite some research done on enzymes, to what extent they can tolerate pressure. And I think it really is protein, so enzyme dependent, what temperatures they can resist. It goes quite high, but I don't know the numbers. But I know that it is being looked at for food applications, to what extent you can include enzymes for certain applications. But I would have to look it up for the details, but I'm pretty sure that there are options there.
All right, we will share contact information of all the speakers afterwards. So also, if we cannot give an answer to your question, please feel free to email them. The last question to finish this part of the program is from Arman. Do you work with many people outside of chemistry, and in what fields?
Yeah, that varies a lot, but indeed, many of the projects in my group are together with other groups, often also with companies in other countries, and it varies a lot. I see the development that in the beginning, when I started my group, and that's often, let's say it's about 20 years ago, the focus for enzymes was a lot on pharma products. But nowadays, not only for pharma enzymes are interested, but also for food, but also for materials, for polymer synthesis, for example. So the application range is much broader than it was 10, 20 years ago. So yes, we collaborate with more and more different groups and companies in the last couple of years.
Right. Thank you very much. I think it's time for our next speaker, Hugo van Beek of Gecko Biotech. Hugo, please proceed.
Good afternoon, everybody. Thank you for inviting me to this webinar. I will talk about what we do at Gecko. Gecko is a startup company located at the Campus Groningen, and we started actually based at the university in the group of Marco Freye, actually. So Marco is still our scientific advisor, and together with Nicola, I'm doing most of the work in the company. And we are working on translating all the fundamental knowledge that has been generated by the group of Marco in the last decades to actual applications that can be used in industry. So we started a couple of years ago actually as more an enzyme supplier. So all these companies that work together with the group of Marco Freye came to the group to ask for larger batches of enzymes, maybe some specific research that has to be done, and other projects that are not purely of an academic interest. And we started the Gecko initiative to see if this would be feasible to start a company on this. This is all based on oxidoreductases. Actually, I will hide this. Which is the main focus of the research of Marco Freye also. And all these enzymes have interesting activities, and I will show the diversity that is possible with enzymes from our portfolio for two classes, for biovillagre monoxygenases and for alcohol oxidases. So these are reactions that are catalyzed by BVMOs. These enzymes are a little bit complex. They use NADPH as a cofactor, as well as molecular oxygen. But then, of course, you also get an enormous amount of diverse reactions that are often very specific and selective. So often, if you make a chiral product, you make only one of them, which is, of course, very interesting and extremely important also for pharmaceutical applications. The diversity is huge, so you can have small substrates like acetone and up to really bulky molecules like progesterone here on the right. Another class that we work on a lot is our oxidases. And also for this class, we have a diverse set of enzymes that can work on aromatic compounds. And recently, the group of Marco Freye also developed an enzyme that can oxidize glycerol, which is very interesting for multiple purposes. And we also have oxidases that are active on different kinds of sugars, which can be useful either from the chemistry point of view, but also because these enzymes generate hydrogen peroxide, they can be used for sensors. So these are the enzymes that we have on offer. But in the last year, since we officially started as a company, exactly 1 year ago, I think we signed the required documents. We offer mainly services based on these enzymes because companies do not need only enzymes, they also need to know how to use them. And often enzymes are not evolved to do the chemistry we want them to do. So what we do a lot are feasibility studies and consulting to see if enzymes can be used for certain processes. Then we can also find the enzymes that are carrying out a certain reaction. We can do engineering on an enzyme to make an existing enzyme do the new reaction of interest. And then often this leads to joint developments where we work together with one of our clients to really get the enzyme from its current state to some form that it can actually be applied. Usually by altering the specificity or the stability, for example, with this Fresco method that Marco introduced. And then when the enzyme has the properties that are required, of course, you want to test this on a pilot scale. And this is also something that we can do. We can make up to 10 liters of cultures in our fermenter, which gives you a couple of grams of enzyme, which then can be used for chemistry up to kilogram scale, more or less. And all these services we offer to, well, everybody that wants to use them, of course. But we find that there are actually a lot of companies that would like to use enzymes because often they are green solutions for different problems. But not everybody has the enzyme specialization in-house. So we also offer training and support so that companies can use our enzymes. One of the backbones of our company is a protocol that is developed for Fresco, which is based on the rapid design of mutations. So the mutations that are designed in the computer are used to design primers, which are then used to build different mutant strains that produce enzymes, which then can be grown in 96 well plates, so in a very high throughput fashion. It can also be purified in this 96 well plates and actually also analyzed in 96 well plates. So very quickly for this Fresco method, we can build, grow, and purify a lot of enzymes and see what they do. So for example, recently we made 380 single mutants in 2 weeks for this Fresco approach. We got 20 significantly improved mutants. And then in the next step, they would be combined. And let's say, hopefully you get all the way up to the boiling point, as Marco showed. But this shows that rapidly you can improve an enzyme. So that's very interesting for actual applications. What we also do now is to use the same pipeline that was developed for Fresco, but then for a different purpose. So often you want to find an enzyme, but you don't know really where to look. So we have, of course, very good prediction capabilities, but still you have to test a lot. So we use the same protocols and high throughput purification methods, but then instead of single mutants, we use whole synthetic genes. So we get a lot of diversity, and we test them with reliable assays to really show that these new enzymes catalyze the reaction that you need. And then Sven asked me before, like, what companies do you work for? Do you work for food or pharma? And also, as Marco introduced, in the past, it used to be only for pharmaceutically active ingredients, because this is where most money is made. This is where you can invest most money in research. This is something that we still do, but we also developed and worked on enzymes for different applications, for example, for assays and sensors, for working on dyes to do fine chemistry, for example, with Syncom, who will be presenting later, but even for biomass valorization, where the value added is not so much per kilo, but where, of course, the scale can be enormous at a certain point. So this is what we do. I hope that you got a good idea of what we can do and what we have been doing for companies. And let's see if there are any questions. Thanks.
Thank you very much, Hugo, for the presentation of Gecko. Indeed, I've got a question, and it's quite a technical one. So here we go. Are you the question is from Lorenzo, by the way. Are you considering droplet microfluidics to increase throughput, or are you interested in doing so?
Nice question. I think this is a very interesting method, and I think there are huge possibilities for this. But what we, let's say at the moment, what is our strength is that we do direct measurements of the reaction products with HPLC. So we like to do this on a slightly larger scale than microfluidics. So our results can directly be translated into applications. And I think this is our strength, and this makes let's say this makes us as quick as we are.
Right, thank you. The last question from Puya. Which oxidase is most popular in biomass valorization markets? Can you give us an answer to that?
So we don't supply direct oxidases for biomass valorization, but the enzyme that we sell a lot is the keto-oligosaccharide oxidase, where we have a mutant that can actually be used to check how good your cellulases are. So this is an enzyme that we sell a lot of, actually.
All right, thank you very much. A packed program. Unfortunately, we have to leave it here with all the questions and the discussion. So we would like to thank you, Hugo, and I would like to give the floor now to Linda Dijkshoorn of Evie Biotech.
Hi, Sven. Good afternoon. And good afternoon, everyone. I hope you can see my presentation now. Yes, that should work. So yes, my name is Linda Dijkshoorn. I'm the CEO of Evie Biotech. And well, you guys can see me. And to link actually to what Edward was saying, I'm sitting right now in the InnoLab Agri-Food. It's a beautiful spot to be. We've been here for 1.5 years now, and it's amazing, beautiful building. To link to what Marco Vrij actually said, I'm finalizing my PhD from the GRIP pharmaceutical department. And what I actually started out with is protein engineering. So the first thing I actually needed to do was to crystallize a protein to get its structure. And that's where my love for protein structures actually started, but also my frustration. And this frustration was actually the inspiration of Evie Biotech. If you look at this really nice little image, this is what you can get when you use a computational tool called molecular dynamics. Well, it's a technique, and then there are a lot of tools to actually show how enzymes would work. You can predict that. And the possibility of actually predicting how enzymes would work in real life, that inspired me actually, because enzymes are what makes life run. And with Evie Biotech, that is what we engineer. We engineer life forms. So instead of actually having to look at one enzyme, we have to look at whole networks of enzymes, because we engineer microbial cell factories that can produce a product. So we use our unique computational pipeline to not just look at the single enzymes, but look at the enzymes within biosynthetic pathways, within the ordered chaos of microorganisms. And so we do this to design these molecular cell factories that basically eat a substrate. We create a new pathway in there, and we have them produce a product. So these are designed to produce molecules to actually be able to produce them on an industrial scale. Now, this method of designing a pathway within a microorganism actually exists for a long time. But what they would only look at previously was just the biosynthetic pathway from substrate to product. But an organism is so much more than that, right? If you just go from substrate to product, all you do is you engineer one single organizational layer. So within our computational pipeline, we are actually building a multi-dimensional model where we can predict how different enzymes and proteins of different regulational spheres are communicating with each other, and taking that into account to find the best biological design. Now you can imagine that if we want to know all this information, right, a genome, a transcriptome, a proteome, a metabolome, that you create masses and masses of data. And this data is quite valuable, but it's only valuable if you can use it properly and if it is combined properly. So one of the other things that we're building in-house is a graphical database where we not only add our own developed data, but we also translate publicly existing data to be machine readable and to be integrated within this graphical database. So yeah, it's a quite complex story. But so when we design an organism like that, we start from the bigger picture. We start from, okay, the organism as a whole, but in the end, the tools that make life run are enzymes. So as I told before, enzyme engineering, we use molecular dynamics to engineer, to create function, to test, to hopefully decrease our laboratory high throughput activities. But there are other tools that are necessary to have to be able to make enzymes work in something else than a in vitro environment. An in vivo environment often poses a lot of different problems. So one of the things that we're developing is a genetic tool, a genetic designing tool that actually reads between the lines. And this reading between the lines can help us actually be able to express enzymes that were usually insoluble and found in inclusion bodies. Unfortunately, I can't tell much more about this because, well, we need to keep it as proprietary knowledge, but it's one of the things that we're working at to make sure that those obstinate enzymes will function properly in our organisms. So that is, in a nutshell, what we do at Evie Biotech, and I'm quite curious what you guys' questions are. Thank you so much.
Thank you very much, Linda. I'm looking at the chat box and I don't have any technical questions at this moment, but I would like to ask you on another type of question. You launched your business, Evie Biotech, on the campus.
Mm-hmm.
How was it for you to start a business at Campus Groningen? Can you tell us a little bit more about that?
Well, I think my story is quite interesting for the potential startups out there in the Netherlands, because I do think that Groningen is one of the most beautiful places to start as a startup. If you have an idea, and this is coming back to the hubs that Edward mentioned before. There's an organization called Venture Lab that actually helps you build your idea into a feasible business plan. They help you become investor ready. There are a lot of investors. Well, right now we're at step one of actually being a company within the InnoLab. We've looked around. There are not that many places where there is a well-priced commercial place to have an ML1 laboratory space to use. So yeah, I think it's a unique ecosystem, and because we're a little far away, I mean, for the Netherlands, 2 hours drive or train ride feels far away. Other countries, it might not be that far away. But since that sense is there, all the companies that are here, we're kind of helping each other out. So for such a young biotech company, we already have a lot of partners and a lot of really experienced entrepreneurs helping us out as well.
Thank you very much. A question from Arman. How do you deal with COVID as a startup in these days?
I think we were lucky because we are 70% computational. Well, 70% of us can work from home without any problems. And the location here, again, is a benefit that we are a little bigger, that there is quite some space in the lab, and the lab is the cleanest place where you can be, right? Everything is disinfected continuously. So safety-wise, we could just continue working. And it also created opportunities. Right now we have a collaboration with the Department of Virology from the UMCG and drug design from Drug to help them out and do some COVID research, actually. So it's very interesting. You know, in each crisis, you can find opportunities to help.
Right. Thank you very much. Also, time-wise, I think we have to push on to the next presentation. Thank you very much, Linda.
You're very welcome.
Please also have a look at the chat during this webinar, and maybe you can interact in that. The next presentation is a dual presentation from a leading lecturer, Doede Biddema of University of Applied Science, Hans Hogeschool, and Professor Gert-Jan Euvering of the University of Groningen. Gentlemen.
Thank you, Sven. I will start. I am Doede Binnema. So as Sven told, I hold a professorship at the University of Applied Science Hanse Hogeschool, and Gert-Jan and I would like to introduce the SAP facility, which was established in Groningen to be able to produce at a larger than laboratory scale for companies and knowledge institutes. Next slide. The facility in itself is part of an ecosystem in the northern Netherlands, where our colleagues in Emmen with Greenpack MTech focus on biopolymer production, and in Leeuwarden focus on food and water technology. Next slide. The ZAP, Zennic Advanced Processing Facility, is established by 3 knowledge institutes in the knowledge chain: the University of Groningen, the Hanse University of Applied Science, and the Noorderpoort Vocational College. The 3 of us established this facility, which consists of a research hall, a laboratory, processing and storage facility, and a greenhouse. Next slide. The idea was to have a facility where we, with companies and companies with us, could scale up the lab results. This from a milligram to a kilogram scale, or for a liter scale to a cubic meter scale. It's mainly focused at valorization of biomass and bioconversion. It's also intended, that's why the 3 knowledge institutes and also 3 educational institutes work together to equip people working in the region with more knowledge and strengthen our education. It helps young starters, and we want to be a hotspot where companies can work together with knowledge institutes and together with students and workers in our institutes. Next slide. To be able for companies to use this facility, we have a so-called rent-a-box model, where you can rent part of the facility and make use of all the facilities in this, the test labs area, etc. People interested in that can seek contact with Rob van Linschoten. His email address is in top of the slide. He is the general manager of SAP and facilitates the work of companies in our facility. Next slide. Here is an impression of the 2 parts of the facility. We have one part where we work together and where students work mainly with projects from companies and from with our institutes, and another part that is shown in the picture below. There we have space where companies can rent part of the infrastructure for a certain period of time or for a lengthy period and work there with their projects. Next slide. And Gert-Jan will now take over the presentation and highlight some of the projects we are running and companies are running in this facility. Gert-Jan, the floor is on yours.
Sorry, I was a bit fiddling with my slides. Okay, so one of the projects that is done with the Hanse Hogeschool and together with the University of Groningen is actually to set up new technologies that involves the extraction of components with supercritical CO2. Professor Francisco Pigioni has a large consortium set up where we do all kinds of research on supercritical carbon dioxide, and the Hanse Hogeschool is involved in this project on the biorefinery of lupin. So that's a plant, and then we will get proteins out of this material for a new food application. The Hanse is the scientific coordinator, and they are going to develop an integrated supercritical carbon dioxide biorefinery. And this is done within the ZAP. So over here, you see a scheme of such an installation. And to show that this installation actually exists, we also have a picture of the supercritical carbon dioxide machine inside the ZAP. Another project we do together is on a project where we are going to valorize side streams of the industry biostreams for the production of a bioplastic. And the bioplastic is called polyhydroxyalkanoates. It's a kind of a different bioplastic than, for instance, the plastics from polylactic acid, PLA. PLA, polylactic acid, is made chemically, but microorganisms synthesizes the monomers, so the lactic acid. In this case, the microorganisms, they synthesize the polyhydroxyalkanoates as granules inside their cells. And the major hurdle in these kind of projects is actually to produce a nice homogeneous polyhydroxyalkanoate. And the second hurdle is to get these granules in a sustainable way out of the bacterial cells. So we set up experiments that we do within the ZAP in a 40-liter fermenter, and that we have sufficient material to actually figure out how to extract the polyhydroxyalkanoates from these cells. Another challenge in this project is that we are not working with monocultures. We are dealing with waste streams, and the size of these waste streams is that high that sterilization of the streams is not very sustainable. It costs too much energy, and we are working with stable mixed cultures that are producing polyhydroxyalkanoates. So we are changing the process conditions that only the favorite mixture will maintain itself inside the reactors. We have a lot of partners involved in this project. Some of these partners are involved in the end project, in the end product, the polyhydroxyalkanoates, to find out what kind of applications they are. And there are also companies involved like KNN Cellulosa, for instance, who are dealing with the substrates. We combine this with lab scale experiments in a 5-liter reactor in our lab. The findings from this lab go into the ZAP, and from the ZAP we go even to some larger scale applications. Another project I'm doing myself with the startup company called Carb Explore. And Carb Explore is dealing with enzymes and substrates with carbohydrates. We have a project which we are modifying one of the components of stevia, and that one of these major components of stevia is called ribodioside A. This compound is for most people quite nice because it has a very nice sweet taste, but for 50% of the population, the aftertaste of ribodioside A is kind of a bitter lingering. And we discovered, or Carb Explore discovered, that if you make a glycosylation over at this position and make from one saccharide, you can make an additional sugar attached to it, that the resulting glycosylated ribodioside is actually sweet for the total population. So we removed the bitter lingering aftertaste of stevia. Well, this is not done in a chemical way. This is done in a biological way using an enzyme which we have mutated at a certain number of positions. And it's a glucan sucrase from a lactobacillus organism. So it's also a food-grade organism. The main challenge is that this is done in the laboratory. And if you want to have a product which is for food applications, you need to have somewhat more. And then you are in the initial phase already thinking in the high kilogram scale for all kinds of testing applications. So at the moment, we are able to produce the enzyme in about 7.5 liter culture. We use 5 units of enzyme in the enzymatic reaction, and that reaction is going quite well. We have 95% conversion, and at lab scale, we can reach a concentration of 150 grams per liter. However, the volume of this enzymatic reaction in our lab scale is only 50 milliliters. That means we can isolate approximately 6 grams of glycosylated ribodioside from our enzymatic reaction. So what we are going to do in a KIEM project that was funded by NWO and the regieorgaan SIA, to come up with a process in the next year to have an enzymatic production of at least 40 liters, but then at high densities. So we are not aiming directly for 400 liters of culture with an OD of cells, for an instance, of approximately 3. No, we are aiming for an optical density of 30, and so that we can decrease the fermentation volume to 40 liters. We use the same and also expect that we can have the same conversion rates, and then we are aiming for a volume between 100 and 1000 liters. So that means we can isolate the product from about 10 to 100 kilograms. And that would mean that Carboxplore has sufficient enzymatic modified stevia for all kinds of applications for future customers. So our focus in that project would be on enzyme isolation. And also, as you can imagine, the price of the enzyme is quite substantial. That we are also looking for the possibility of recovering the enzyme from our enzymatic reactions. Hopefully, the conversion would be in the area of 90 to 95%. And last but not least is the downstream processing. So how to get your glycosylated stevia out of your enzymatic solution. For this, we use SuperPro for the modeling, and we can do quite easily mass balances with SuperPro. But this is just an example of a process, how such a thing looks like. It's not the actual process, but it can be also combined with an economical analysis on the end product and also of the different waste and side streams. For this, we are going to set up a new bioreactor within the sub facility, and it will be installed somewhere over the summer or in the early phase of Q4, quarter four of this year. But hopefully the corona crisis would not interfere with our plans. We are going to make an 1 cubic meter enzyme bioreactor for our conversions with stevia. So you can also use this, of course, for halfway, and then we have a nice volume to do enzymatic reactions. This one will be expanded with a cross-flow filtration unit, so that we can also use nanofiltration, ultrafiltration to recover the enzyme from our enzymatic reactions. These are our plans. We are quite far at the moment, but in the lab we are setting up the high-density fermentations. We have done previously already quite some work on the conversion, and also on the lab scale purification of the glycosylated stevia. And the challenge is, of course, in the upscaling. Well, with this, I would like to end my part of the presentation, and are open for questioning or other remarks. Sven, floor is back to you. I don't hear you, Sven.
Good job in putting a lot of information in those 10 minutes. I will have a quick question for you. And I think it's about the facilities. In the presentation prior to this one, Linda talked about this about the InnoLab AgriFood. You present another facility, the Zenic Advanced Processing facility. How do those two facilities align with each other? Can you tell us a little bit more about that?
Well, if you saw the volumes in the presentation of either Gecko and from Marco and also from Linda, is that they perfectly combine. So we go the next step. So the ZAP facility is not modifying enzyme, is not modifying organisms, but we are looking at the bioprocess technology to actually cultivate these organisms on a larger scale and to model the whole pilot scale processes.
All right, thank you. I see a couple of other questions arriving in the chat box. Sorry, we have to proceed. We would come back to you on that.
Okay, that's fine.
Thank you very much, Gerjan. The next presentation, and also the last, if I'm correctly, is from Elena Herrero Gomez, business developer at Merchem Syncom. And she will go a little bit more in detail about chirality and enzymes. I hope you're ready for it. I hear you already.
Yeah,
the floor is yours.
Thank you. Thanks, Ben. So yeah, good afternoon, everyone, and thanks for joining this webinar. I'm Elena, and I'm here with my colleague Ana Rios. Ana is one of our experts in enzymatic catalysis. And what I want to show you today is some examples where really enzymes help us to access complex chiral molecules. First, I want to tell you a little bit of who we are. We are Merchem Syncom, and we are a contract research organization specialized in organic chemistry. What it means is that we perform research for different companies, so like, for example, for big pharma or small or even virtual biotechs. We have been around for a while, so we've been around for more than 30 years. So you can imagine that we have collected a lot of experience in different kinds of chemistry. And currently we are 400 chemists, and 60% of them are PhD. Our activities cover drug discovery and early development. So that means that we are active from hit finding to the manufacturing of the GMP batches to support phase 1 and phase 2 clinical trials. And as I mentioned in this presentation, I have selected 3 examples in which enzymes were really key to the success of this project. So the first one I find particularly nice because we did in collaboration with one of our neighbors here in the UNCG, actually the group of Dr. Pulanens that was mentioned in the previous presentation by Marco. So the target in this case, we wanted to prepare this complex aspartate derivative. And there was some literature precedents, but the synthesis, they were all or very lengthy, so 20 steps, or they were shorter, but the enantiomeric excess that you could achieve was not really good. So what was key to develop this new synthesis was this Lias enzyme that was developed by the group of Pularens. And this enzyme was able to catalyze very efficiently the addition of ammonia in this double bond. So with this key step in place, it took us only 3 steps to arrive to this key intermediate 3. And from there, in 9 steps, you could access target molecule, but also family of derivative in good yields and also very good enantiomeric excess. Another example that I would like to show you is this oncology drug that was developed by Pfizer. We don't have enough time to go through the whole synthesis, but what I'm showing here is a key retrosynthetic step. So you can, one of the steps was this Mitsunobu coupling between the nitropyridine and this benzylic alcohol 2. And the challenge here was to obtain this benzylic alcohol 2, again, in good quantities and good enantiomeric excess. So you can see quite easily that you could have this by reducing the corresponding ketone. But unfortunately, all the methods that were tried, either chemically or enzymatically, they were not successful. So we had to go around it, and what we decided to do is to do a kinetic resolution starting from the acetate protected alcohol. So several enzymes were screened, and finally the pig liver esterase was the one that was doing the trick. And actually this reaction worked in a very decent yield, considering of course that you always get 1-to-1 mixture of these 2 products, an excellent enantioselectivity, but also the undesired enantiomer could be racemized and submitted to the reaction conditions. So then eventually it was a very efficient process that allowed to produce multi-kilo quantities of this intermediate 2. And this was really important to support the early phase clinical development of this compound, which eventually made it to the market, which is great. Another example is that I want to show you is this one that was recently published, actually also in collaboration with Pfizer. And I find this is also a very nice example where you can see that you can revisit all chemistry using modern technologies. So in this case, we were interested to produce this alcohol 6, and this was described. You could do that by the photooxidation of cyclopentadiene, followed by acetylation, and then monodeacetylation using an enzyme. So the problem with photochemistry actually is that it's very difficult to scale up. The light doesn't go well through reaction mixtures, so that's really a problem when you need to, especially when you're working in bigger vessels. So how we solved this problem was using continuous flow chemistry. So we designed and we built this reactor in which we could perform this singlet oxygen oxidation very efficiently, and we can access gram quantities, multi-gram quantities of this diol 4. This could be acetylated, and then we focus also our effort in the optimization of the enzymatic step using Novozyme 435. And the focus in this case was not only to get a good anti-selectivity, but also to be able to increase the substrate concentration to have multi-gram quantities. And this was actually performed by Anna, and it was also very successful, and we could access this compound in also multi-gram quantities. So these are a few examples of what we can do, and I hope you find it nice. I hope you find it inspiring. But maybe you're thinking about the reaction that you are having troubles with, and I want to invite you also to come to us and share these problems with us. So we have people like Anna that has a lot of experience, and also we have a very nice catalytic screening system where we can screen different type of catalysts, biocatalysts, but also heterogeneous and homogeneous metal catalysts. And with this, I want to conclude my presentation. I want to thank Sven for the invitation, and also all of you for your kind attention, of course. And I'm happy to take any questions.
Thank you very much, Elena, for the last presentation and going a little bit deeper into a really chemistry topic regarding enzymes. One question for you.
Sorry, Sven, I couldn't hear you.
Do we have a technical problem? How it's now?
Now I can hear you.
Nice, then I will start all over again. One question from you is, you're working for a bigger company, especially an SME Plus company, but you're located on campus.
Yeah.
How is that for you?
No, it's really great. I mean, because we have this, as it was mentioned already, this ecosystem of companies with different expertise. And it's really great because we are specialized in organic chemistry, but if we need to know anything more about enzymes or whatever other topics, then we have our neighbors just across the road that we can go and just discuss the projects and have collaborations if it's possible. So I think this is really, really nice environment for the ideas to grow, actually.
All right, thank you very much. The last question, a technical one, maybe also for your colleague Anna. Lorenzo was asking, are you using enzyme cascades?
Hi, Lorenzo. Thank you. Well, it depends on the projects, because I mean, here what I show is only the things that are published, because 99% of what we do for our clients is confidential and we cannot show. But maybe Anna want to comment on that?
Well, at the moment, we never had a project in which a cascade was really necessary, but of course, it's something that we can, it's always depending the kind of project that arrives to us. So it would be a very nice alternative, because you always decrease the synthetic route, the steps, if you use a cascade reaction. So yeah, please, I would like also to invite people to send us enzymatic projects, because we have some, but we really enjoy them. And also we would like also to collaborate with companies as Gecko. So we have some projects with them as well.
All right, thank you very much, Anna. I also have a look at the clock, and I think it's time now to wrap up the seminar, of this webinar, I should say. I think the hour was packed, but just we showed you the tip of the iceberg of what the ecosystem of Campus Groningen regarding enzymes comprises. I can imagine you have a lot more questions for us than we could answer in this hour, so please feel free to send all your questions to my email address, that is sven@campusgroningen.nl. I can also imagine that you have something to tell us, that you have something to show us, that you have an added value for our enzyme ecosystem. So are you ready to join our ecosystem? I would like to invite you to send us your pitch, also to the same email address before the 22nd of May, and have a chance of winning of some great vouchers, like business development support from the campus community, also some discount on our facilities, like mentioned, the InnoLab Agri-Food and also the ZEP facilities. And to make that a little bit more concrete, the discount voucher comprises, if you are developing a one-year project, you get the first 3 months rent for free. So I hope that is I hope that inspires you to get in touch with us also after this webinar. And this brings me to the last slide of today. Thank you all for watching. Thank you all for being here. If you have more questions, send it to us, and we hope we meet again in another event or webinar. All right, thank you for now. Take care.